Claudio's already shown a little bit of what we're about with Objective Team 2, monitoring carbon and nitrogen dynamics for cropping systems here in the Northwest. Before I get started, though, I want to acknowledge the really super degree of collaboration we had within our Objective team. And I think it's a reflection of the type of collaboration we had across the whole REACCH project. But it's really been fun to work with everybody within the team and with the other Objective groups as well. Everybody just had an attitude of let's work together and let's get this done, and it's really been a good experience. So picture yourself as a member of our Objective team 6 years ago, and you're standing at the edge of this field, and you start to ask yourself some pretty specific questions, scratching your head, wondering, okay, this looks like a pretty healthy field. It's obviously taking up a lot of CO2 through photosynthesis. What happens to that carbon? How much of it is respired back to the atmosphere? How much of it is taken up in the soil? How much of it might be lost due to wind erosion or water erosion? So these were the kinds of questions that we were looking at as we started the project 6 years ago. So is atmospheric carbon actually stored or lost within current wheat cropping system? And how does management affect that balance between uptake and loss? Also, we're interested in nitrogen, specifically nitrous oxide, a greenhouse gas. What are the current emission rates for N2O? There have been very limited measurements of N2O emissions in the Northwest up to this time. How do no-till practices affect N2O emissions? Can we do something to affect how much nitrous oxide is lost to the atmosphere? And then how much carbon and nitrogen are lost due to wind erosion, something that's part of the whole carbon-nitrogen dynamics within these fields. And similarly, how much carbon and nitrogen are lost due to water erosion. And how does tillage management and climate change affect these losses? So what we were trying to do was to actually make measurements to provide a foundation for understanding and trying to answer these questions. And that foundation then, as Claudio shows, provides a way to look forward and to project how these things might change in the future. So look at the atmospheric side first, and then Erin's going to come up and share the presentation and talk about the water and wind erosion. How did we tackle these questions? Well, we didn't know how at the beginning, but we figured it out. We deployed 5 flux towers at different sites across the region. And we were able to run these continuously year-round and ended up with 16 site years of data for these different locations. And it basically gave us a way to watch these fields breathe day in and day out over the course of multiple years with different crop rotations. So we end up with this sort of time series of the carbon dynamics. And more importantly, if you look at the larger diagram, here we're looking at the uptake of carbon on the y-axis and the loss of carbon due to respiration on the x-axis. And if you have points that fall above this dashed line, those are fields and crop rotations where there's a net uptake of carbon, or the carbon balance favors uptake. If they're on the line, then that's sort of a carbon neutral sort of situation. And what you find is it's the winter wheat crops that tend to have a net carbon uptake, and the spring crops tend to fall closer to the line where it's neutral or even possibly a slight carbon loss. So that's a pretty significant finding. And I think this diagram is really a nice summary of what we gain by deploying these towers. We've got multiple sites, multiple years that tell us something about how carbon is taken up and lost in these wheat cropping systems. And so if we look at this, we have one of the first multiple site, multiple crop rotation data sets for wheat-based cropping systems. The winter wheat crop years showed a net carbon uptake. Spring crop years exhibited a carbon neutral balance or a slight carbon source. We had lower carbon dynamics, basically respiration and uptake for the low rainfall winter wheat fields compared to the higher rainfall winter wheat fields that we looked at. No-till management resulted in lower carbon respiration and water losses compared to conventional tillage. At the irrigated site where we made measurements, we saw large amounts of carbon and water losses into the atmosphere. And as Claudio already showed, the data were really useful for helping to evaluate and understand how CropSys works. We also made N2O measurements. Sarah Waldo is back in town to join us today. She was responsible for these measurements. We used a hybrid system where we used chambers plus a gradient flux tower method at a conventional till and no-till site. And basically we found annual estimates of fluxes that were much larger than the IPC regional estimates for our region. And this just suggests that we need to keep making these measurements and really confirm that that's what's happening. And now I'll let Erin talk about the water side of things.
All right, yeah, I think Sanford gave a little bit of an overview of the 5 years that we were monitoring, and it was kind of a unique 5 years in the sense that we got a lot of the extremes, and I've just see some of the numbers. We had 2011, probably one of the wettest springs in the last 20 or 30 years. 2011, which led to massive amounts of fallow ground in the high precipitation zone. Like in Latah County, you saw a lot of people didn't get spring crops planted. It was just too wet to get on the fields. And that led, in 2012, we had a higher than normal precip year as well. We had massive amount of runoff, a lot of erosion that year. I didn't show this data, but I monitored Paradise Creek out here, sediment load, and that was the highest sediment load since 2000, since I've been monitoring sediment load. So we had some major wet implication, wet year and major implications on sediment transport and carbon. Now we come to 2014, much drier than normal year that we had, major warm temperatures in May and June, a lot of heat stress. You can actually look at the Palouse River stream flow and the North Fork Palouse River at Palouse, and you plot stream flow, and the summer stream flows were probably the lowest you've seen the Palouse River get in probably 30 years as well. So we had these wet conditions, we had these dry conditions, so it's probably a unique 5-year period of what's likely happening. So what I'm showing here is actually runoff from a conventional till, the Moscow Mountain site, in red versus a no-till site at the Cook Farm here just outside of Pullman, Moscow. And so you've seen this wet year, 2012, surface runoff well higher than any of the remaining years. And so we had major surface runoff, major erosion going on. At the no-till site, we saw not as high. This is actually from a artificial drain in the field, and we see a pretty consistent runoff coming through there as well. But if you look at no-till versus conventional till in both these sites, interestingly, the magnitude of runoff, if runoff and excess water is about the same. So we're having about similar excess water. One is coming through tile flow, one's coming from the surface runoff, which had major implications on how much sediment we actually got from both sites. So no-till greatly reduces the amount of sediment and the carbon being transported off the site. There's more residue. It makes sense, and we saw that in the data. Interesting, like dissolved organic carbon in the no-till was about twice as high as what we were getting out of the conventional till. So we're generating carbon in these no-till fields. We're actually losing some as well through dissolved transport. We know this in sediment. We see this in carbon as well, is as you get larger and larger scales, from the field scale to the basin scale, we see deposition of sediment and carbon. You see storage in places, and so we notice that in our monitoring. Modeling, and this is kind of the interesting thing, builds off a little bit what Claudia was saying, what John was saying. If we do modeling to say how's it going to change in the future for water erosion, we see an increased erosion. And why is that increased erosion? One, you can see there is slight increases in the precipitation in the winter. That could lead to more increased winter erosion. We also see, in the case of lower crop yields, there's less carbon going to the soil organic carbon drops, and then you actually see the erodibility of the soil goes up. And so that also is a complex thing. And the CO2 fertilization, as the transpiration use efficiency, what Claudia was saying, the crops are being more useful of the water they have, that actually leads to conditions where you actually have excess water. And so you could actually have more excess water and could lead to more erosion as well. So this whole future climate, we could see these drought conditions, but at the same time, we can see more seasonality, may see more erosion going on as well. Not to mention it's a little bit difficult to predict how the intensity of the precipitation is going to change, but a lot of predictions are it's more volatile. We will have more increased, higher intensity rainfall, and so that would also lead to increased erosion. Wind erosion side, a lot of the wind erosion studies were done on the drier part of the region by Brett and Schraut, and we see nitrogen losses up to 1.2 kilograms per hectare across different events. Annual losses about 5 kilograms per hectare. Here, again, a data set that wasn't available before this project started. Just to kind of give a synthesis of what do we see then? Okay, we have these atmospheric exchange measurements with the eddy flux measurement. We have water, we have sediment. Let's just look at carbon. And so now we have actually data on all the different major pools and losses. And so if you look at soil carbon, where is the carbon? How much carbon's in the soil? Well, it can range from, and even Dave was kind of showing on the Cook farm, this could be as low as 5,000, but up to 30,000, 5 to 30,000 grams per square meter in the top meter and a half. There's a lot of carbon stored in these soils. And the lower end, it's your clay knobs that don't have a lot of carbon. On the high end are your deep, probably places that actually got sediment and carbon deposited from historic erosion. And so we have some variability. Look at water transport. We're looking at 0.1 to 6.9 grams of carbon per square meter. For wind erosion, it depends on where you're at. If you have a lot of good cover, then you're actually on the lower end of this, 0 to 4, essentially. Carbon loss to the atmosphere, respiration, how much is actually respiring? We're at 400 to 1,200. So the majority of our carbon, if you look at carbon transport, it's respiration, and contrary, and what's what Brian was showing, it's uptake. So we're uptaking carbon through photosynthesis, we're releasing it through respiration. So that's mainly the main fluxes. And these smaller ones, and these oftentimes balance each other. And so these the erosion by wind and water manifest themselves as kind of a balancing, and you can actually see deposition and storage. And so these may seem small, but since they balance themselves out, sometimes the difference is actually in the water and wind transport. Future directions, a lot of this research that we're doing, with especially the eddy flux measurements and as well as the hydrology, is we're building off this and working with Dave Huggins and the ARS on the long-term agroecosystem research site at the Cook farm. And so we're actually taking these towers, some of these hydrologic measurements, and focusing them on paired studies and looking a lot on different diversified cropping systems and specifically fall-seeded crops. There's going to be opportunities potentially with these winter precip, maybe some excess water in cases that we can do at more intense cropping systems. As we do more intense in cropping systems, we likely will increase the amount of carbon we're storing in the soil. And so we can see these kind of feedback loops coming on each other. So I will stop there.